Hi, my name is Stuart Wienig, and this video is about how and why to use the application mapping feature of CA Network Flow Analyzer, also known as ReporterAnalyzer. My blog at stuart.wienig.com has all kinds of cool stuff about all the NetQS products. I currently serve as the communications officer for the CA Infrastructure Management Global User Community, and I've been working with the NetQS products since 2006, doing just about everything at over 150 different customer sites. Let's talk about what NFA does. The architecture is diverse, but there are several main components. The first line of components is actually comprised of your routers. When you enable NetFlow on a router, it tracks all the conversations going through the router and caches the information like the source IP address and source port, the destination IP address and destination port, through what interface the traffic came into the router, through what interface it's supposedly going to leave the router, TOS values, AS values, and so on. Version 5 NetFlow captures a whole lot of information, and version 9 is even more detailed because it's extensible. So, the router caches all this data in the route cache, and then we configure NetFlow to export all that data out to NFA, particularly to the harvester. The harvester receives all of the flows from all of your routers, and you can have multiple harvesters depending on the size of your installation. Now, if you have multiple harvesters, then each router should send to only one harvester. Most of the time this is done by location or region. The harvester receives the flows and then does some processing of the data. And when it receives a flow from a router, the harvester will do an SNMP discovery of the router and the interfaces. And whenever we start sending NetFlow to NFA, NFA responds with an SNMP query to the router. The main reason it does this is that NFA needs the interface names for the interfaces on the router from which it's receiving flows. If we look at the reports, it doesn't really help to see the IP address of the router and the if index of the interface. SNMP polling gets the names of the interfaces for us. The other important thing that NFA gets is the interface speed or the bandwidth of the interface. That's actually a pretty crucial one because without the interface speed or the bandwidth, NFA can't calculate percent utilization. We have to calculate percent utilization, so NFA needs the bandwidth and it uses SNMP to get that. After the harvester has done some processing of the data, there are three types of data: 1-minute data, 15-minute data, and flow forensics data. And depending on your architecture, the 15-minute data is either stored on the harvester or the DSA, and we'll talk about the DSA in a moment. The next piece of the architecture is the master console. The master console is the central hub for NFA. And the master console gives users access to reports and administrators access to configuration. The data storage appliance is only for 3-tier installations, mainly those legacy installations, and it acts as the final repository for 15-minute data. Now that we understand what NFA does and some of the major components, let's look at application. Application mapping is a method of classifying traffic in NFA. NFA has a default method for classifying traffic, but sometimes that needs to be augmented. Now, application mapping is used for two different scenarios. The first scenario is when you have one application that uses multiple ports. Two examples of this would be Exchange or VoIP. Another reason to use application mapping is that we have a bunch of applications that all use the same port, but we don't want to report on them together. An example of this would be web applications. There are a whole lot of web applications out there, and the number's growing day by day, and they all use TCP/80 or 443, and we don't necessarily want to report on them all together. So, what we can do with application mapping is create rules that uniquely identify traffic either by IP and subnet, by TCP or UDP port, by TOS value, or any combination of these, and we can reclassify that traffic. Instead of saying that this traffic came in on port 80, we can reclassify that to some other port number. A great example of a single application that uses multiple ports is Cisco Voice. Cisco Voice uses even-numbered UDP ports above 5,000. So every time you pick up your Cisco phone and dial a number, you're connected to the other phone on UDP port 5002 or 5004 or 5006. Every single call would use a different UDP port number. Now, since NFA classifies every conversation by TCP port or UDP port number, every single phone call would show up as a distinct protocol. There are problems associated with tracking that many different protocols. An application mapping rule would say, if I ever see traffic using TOS 8 or TOS 16 or whatever TOS value is associated with your voice traffic, instead of labeling the conversation as UDP 5002, UDP 5004, or UDP 5006, label it as UDP 65,000, some high number unlikely to be used by any other application. All the traffic for those phone calls then gets put into one single bucket. It all gets reported as one single unit because that's what it is. It's all VoIP traffic. So we'd create a rule by toss, and I'll show you exactly what we would do for that kind of rule. Something to remember, now this only affects the port number classification of that conversation. The original IP addresses involved and all the other data contained in the flow is unaffected. So you'd still have the visibility into which individual IP pairs participated in the conversation. Let's see what that rule would look like. Let's say, for example, that my VoIP control traffic uses TOS 8 and VoIP data uses TOS 16. This information should match the QoS configuration in Cisco Unified Communications as well as the routers on my network. The first rule would say if TOS value equals 8, that's VoIP control data. Classify it as 65508. I usually use 65508 because TOS 8, 65508. And then my VoIP data rule would say if TOS equals 16, classify it as 65516. Now this means that all my VoIP traffic, regardless of whether the original port was 5000, 5002, 5004, it's all going to show up as 65508 or 65516, depending on whether it's control or data. Web applications are a good example of multiple applications using the same port. Outlook Web Access, SharePoint, a web order application, they all use port 80, but they're not part of a single application. They shouldn't show up grouped together as one single protocol. If they all show up grouped under HTTP, then the only way to tell the difference between these applications is to actually drill into the protocol and look at the hosts or conversations and determine which server is involved. Application mapping rules take the web applications and split them out into individual buckets. The way we uniquely identify this traffic is with a rule that says, if it's on one of my Outlook Web Access servers and it's port 80, classify it this way. If it's one of my SharePoint servers and it's port 80, classify it that way. If it's one of my web order servers and it's port 80, classify it this other way. Let's look at what those rules would look like. Outlook Web Access, the SharePoint portal, and the Web Orders application would each have their own rule, keying on an IP address and a port number. Each rule would remap them to a new port number. For Outlook Web Access, the rule says if it's either of these two IP addresses on port 80, instead of showing it as port 80 traffic, reclassify it as 65501. For SharePoint, for these SharePoint servers, whether on port 80 or port 443, for example, in my case, maybe it doesn't matter, reclassify it as 65502. And for web orders, for port 80 on my web order server, reclassify it as 65503. So this has been my presentation on CA Network Flow Analyzer and application mapping. I hope this video has been helpful. Subscribe to my blog over at stuart.wenig.com for more videos to come in the future. Thanks and have a great day.